Thanks, Ken. And thanks everyone for coming this morning, despite it's a weekend and it's the very last day of the workshop. And let me begin by thanking the organizers for organizing this conference. It's really nice to see different people, and especially experimenters that I may not usually communicate with and then learn from them. And today I'll be talking about these topics about symmetry indicators. And I apologize for the incredibly fake title here. I'm basically saying that I'm just telling you what I'm not going to talk about. I'm just saying, oh, it's not going to be this time. Because the main reason why I had such a fake title was that I was not very confident that I have anything presentable when I provided organizers my title, but then now we are a bit more confident. So today we're talking about basically how do you use symmetry indicators for finding topological superconductors. And as you can see, we just have many question marks here, so hopefully this will appear in a couple of days. But then it's obvious that this is the first time we give this talk, so it may not be super coherent and whatnot, so just stop me if something is really unclear. And this work is done with Haruki and his student at Tokyo, and in particular, Spatial did all the hard calculations, so it's really good. So I imagine most of you have heard about these names like symmetry indicators and whatnot, but then just let me start with a very, very brief recap. So unless you're a really deep philosopher, if not, I think we can agree on this tautology that the universe is basically split into trivial and non-trivial. And dear physicists though, so we'll try to decorate this and say that when you have symmetries, then you can split the non-trivial class into different varieties. So in our context, it could be strong TI, weak TI, GCI, higher order, and whatnot. What might not have been so appreciated in the past was that even in the trivial case, you actually can also split it because of some percent symmetries. And that's also mentioned by Aslam in the previous talk. And just to be a little bit more concrete, this particular universe, if I restrict it to just the discussions about band insulators, then the more general set would be all possible band insulators. Something like a band structure with a gap, and then you fill your electrons up to the gap. And the subset of trivial states would be things that are really atomic, so there's like a real space localized description of the problem. So these are the trivial things that we usually call atomic insulators. And the idea of symmetry indicators is to say that this kind of picture, if you restrict your attention or if you restrict your information to only the symmetry representation, then it becomes very easy to compare or to understand the structure of this diagram. So because this is a weekend, I think we can be a little bit more lighthearted. And so we'll consult Winnie the Pooh on how to do these things that are claimed to be easy to compute. And the idea is that all we are going to do will be to count. So even Winnie the Pooh knows how to do it. And the counting works this way. If I give you a general band structure, it can look extremely complicated. So this is taken from some paper in 1974 about silicon carbide, which is reasonably simple by the standard of modern material science, I guess. And even in this case, of many bands, they disperse in this way or that way. And in the old days, they used to label every symmetry representations in a very conscientious manner. So at gamma point, they say, oh, this is gamma 1 representation, gamma 1,5, and so on and so forth. So if you just look at this, it looks like you have a lot of information. But then for our purpose today, all you really want to do is to do a simple counting. So I've boxed here a set of bands that are isolated from above and below by some band gap. And then all I'm going to do is to say, look at gamma points. And I would say there are 3 possible choices in terms of representation. It can be gamma 1, gamma 1, 2, or gamma 1, 5. I look at my set, I would say I have only 1 copy of gamma 1, 5. So I'll put 0, 0, 1 there. And then I do the same kind of counting at the sigma line, so it's a line. And then I would say I have 2 options. I have 2 copies of sigma 1 and 1 copy of sigma 2. So I put 2, 1 here, and so on and so forth. And there's one last digit, which is like the total number of bands, which is 3 here. So it's really just counting. And the statement about symmetry indicators is that if you do these countings, you can actually perform the comparison I've tried to allude to. So once you write everything in terms of these factors of representation counts, then you can compare them with the trivial options simply by doing some linear algebra. But then, before I move on, let me just make a quick remark, which is that counting is a very rough check in a way. So we need to count his honey pots. That doesn't mean that there's any honey inside. So you can count, you get some information, but then you should always be a little bit more cautious. So that's also the idea about these symmetry indicators. So basically, we claim that it's something very easy to compute. It's just some counting is essentially linear algebra. And in that sense, it's very powerful, because to find some topological materials, I don't actually need to do any wave function integrals. So the old way of doing it, if you have some DFT band structure, it's very hard to compute it far from the first principles. But here, you don't need to do that. And even more, we don't even need to have any a priori knowledge on phases or invariants. So in fact, it happened to be the case that we found something that we think is non-trivial. We had no idea what that is. And then half a year later, people realized that it's a higher order TCI, which is basically the phase realized divisor. So we kind of knew that has to be non-trivial in terms of just the representations. It takes us, we only learned about the fact that it's something higher order because of the further development in the field. So this is powerful in that sense, but then as I've tried to caution you on, so this is not going to give you a complete classification in general. So because we're only looking at the counts and some information is lost. But then this can be tightened up or sharpened into some mathematical framework and can show that this will inherit part of the group structure of the full classification. So the theory of symmetry indicators is basically what we tried to develop in this paper. And before I move on, I'd like to acknowledge that very similar ideas have been developed in this paper by many people in the audience, though some of them might have left already. So I'm sure you know this is like a paper by the Princeton and Bilbao collaboration. So that's like a recap. It's just whatever we had maybe 2 years ago. And now let me move on to the main discussion today, which is what happens if I try to use these ideas for superconductors. Of course, you can ask a much more ambitious question of talking about generic interacting superconductors, but let me not do that. I'm going to restrict my attention to superconductors that are described within some BDG framework or a mean field description. So in the general case, you still have some kind of band structure. It's going to be particle-hole symmetric. But turns out what is really hard about this problem is to properly identify what is the trivial state. So let me move on to talking about that. So here's the outline for the talk today. I will first try to define what the trivial superconductor is, and then talk about how to get symmetry indicators, and then finish with some examples. So let me also point out that we are very much inspired by these two works that came out in the past 2 or 3 months. So they basically give us an idea, or they basically outlined how you should define trivial superconductors for the purpose of symmetry indicators. So the question is, what is a trivial superconductor? And let me try to motivate a definition by some examples. The first example will be just a boring insulator or just a vacuum. So I will say, I'll write down my Hamiltonian. It's just the chemical potential, basically. So on every side, I just put down some C-dagger particle number. So if it's minus sign here, then it's an insulator. A field insulated, if not, it's a vacuum, if it's a sign. And if we rotate to some Majorana basis, just because we were trying to talk about superconductors, then you can also write this term basically as I gamma gamma bar. So these are two species of the same site. And most of you will probably know that this is nothing but something like a fermion parity. So if I just stare at this example, I will conclude that first, I really want to say this is trivial, because your discussion is kind of screwed if you would look at this and call this non-trivial. But at the same time, maybe this will motivate us to define a trivial superconductor as something like a sum of local fermion parity. There are local objects, they commute with each other, and then you will say, oh, I know the fermion parity that is 0 or 1, then maybe that's like the trivial limit. And Philip is actually shaking his head, so he knows what's his next slide. So let's ask what is a non-trivial superconductor. So the example, the canonical example, will be the Kitaev chain. So it looks a bit more complicated this way, but if I again go to the Majorana basis, it's almost identical. So let me just contrast that. So this one is I gamma x bar. This one is I gamma x plus 1 bar. So they look extremely, they're basically the same in terms of the form. The only difference is the shift in the site index of the next one. And you can show that this is still a parity operator, and they all commute, and so on and so forth. So this is a canonical example of a non-trivial superconductor, but that is still a sum of fermion parity. So that was going to tell you that this kind of rules of saying like sum of local fermion parity is really not a good definition for a trivial superconductor, so we need to do a better job. But it's also quite interesting in relation to what Aslam was talking about just now. It's like zero-dimensional surface states are basically what happens here. And then the high-dimensional version is actually interesting, and we're not extremely sure about all the structures right now. But then let's try to do it again. So we are trying to answer the question, what is a trivial superconductor, right? And on the left-hand side, I now try to show you something like a more generic BDG Hamiltonian than the band structure. So you have the normal part and the pairing part. And one reasonable rule is to say that my superconductor is trivial if you can smoothly deform it to the vacuum. So in the vacuum, we know exactly what it is. So the vacuum Hamiltonian can be written this way. Basically, only the whole bands will be below E being 0, or equivalently, you can just start with like a vacuum and then you just double it in the BDG formula, so this is the best what you'll get. So you can say, fine, I will define my trivial state to be anything that's smoothly deformable to the vacuum. That's basically the K-theory definition, in fact. But then for physics application, especially in the presence of crystalline symmetry, that may not be the best definition for trivial superconductors. And the reason is as follows. If I started with something which is a trivial insulator, so contrast the left and right, the only difference is really the sign of the Hamiltonian, right? So on the left-hand side, I'll just say that any state below energy 0 will be filled. These are the electron bands. And on the right-hand side, you'll say that it's basically the whole band. So if you just have internal symmetries, you can smoothly deform left and right between each other. But in general, once you have some spatial symmetries, this is actually not doable generically. So maybe these really trivial states, if I take the previous definition of deformation to vacuum, they will look non-trivial. So again, this is not the perfect definition for my purpose. And to see why there could be such obstructions for smooth deformation because of spatial symmetries, then I will have to show some slightly complicated formulas. But I think it's the most complicated slide of the entire talk, so bear with me. So I start with some BDG Hamiltonian and normal part and pairing part, and we want to now analyze what happens with spatial symmetries or how spatial symmetry acts on that. So we know what they do on the normal piece. So basically you take your Hamiltonian, the block Hamiltonian as some momentum k, you conjugate it by the representation of your symmetry G, and that would relate you to the Hamiltonian at momentum G, the point group part of that. So this part is just whatever we did with regular insulators or regular band structures. And in the BDG formalism, I double it and then I put the conjugate and minus k here. So you do the same thing. Basically, you just put the star everywhere in this equation and you get that. So very naturally, the symmetry representation on the BDG Hamiltonian would be to say the first block, you do whatever you did. In the second block, you do the conjugate version. So that's just the meaning here. Except that here you have an additional U1 phase difference between these two. If your Hamiltonian is really just the original one without any superconductivity pairing, then this phase is whatever you want to put there is kind of invisible. But remember that the BDG Hamiltonian is, these two blocks are connected by the pairing. And in fact, this chi now has some physical meaning. It's really how your superconducting pairing order parameter is transforming under the spatial symmetry. So you can try to work this out. If you demand this BDG Hamiltonian to be symmetric under this spatial transformation, then you have basically this pairing order parameter transforming as kgk rated by this chi g star here. So it's slightly more complicated what this chi g can be. Maybe it's some representation of the point group, or one-dimensional representation of the point group, and so on and so forth. But for most of my talk, I'll just focus on class D3, which is spin-fold electrons with term reversal symmetry. In that case, this is really required to be real. So the only two options would be chi being +1 or -1. So that's how spatial symmetries act in the BDG approach. And now we can stare at this and realize that physically, this part is corresponding to the electron states, and this is really the whole states. And the chi-g has the physical meaning that we can actually change the relative representation of the electron band and the whole band. And to be a little bit more concrete, let me just start with this one-dimensional example with only inversion symmetry. So this is like a theoretical trick in which I say I imagine I have a boring insulator, but I declare I have some superconductivity. So it's like a purely theoretical gadget. But then on the left-hand side, I just have the usual boring insulator, one-dimension inversion, and I would say maybe the representations of inversion would be positive parity at both 0 and pi. So that's just the original case. And now imagine I magically can add superconductivity to it, such that I'm forced to use the BDG formalism, at least formally. Then there are two options for the inversion representation in terms of the pairing order parameter. It's either even parity or odd parity. So even parity case would be taking a positive sign here. And if you recall this equation in which the electron band and hole band are related by chi, basically at zero momentum, this is positive and it's even parity, then it's still positive. And at pi, it's positive here and positive there. But for the odd parity case, because of this chi, which is -1 here, the electron band and the hole band, the representations are really off by -1. So effectively switch the parity. So this is positive here and minus there, and same there. So now let's focus on the odd parity case. And we'll just try to look at the two cases of fully filled versus the vacuum. So on the left-hand side, it's still some trivial state, it's just a fully filled atomic insulator. On the right-hand side, just a vacuum. But because of the choice of the odd parity superconductivity, we see that the parities do not even match up. So if you try to tune some parameters in your Hamiltonian to go from the fully filled state to the empty state, you must have these minus and plus exchanging their position, but then they don't have the same representation. So when they touch, they actually cross each other. So basically, you must get a gapless space, or you must get some gapless form when you try to deform from left to right. So this is one example in which just because of the presence of spatial symmetries, you realize that the full state and the empty state, they are no longer smoothly connected in general. And with all these observations, then we can now motivate the definition of what is a trivial superconductor. And let me just emphasize again that these were pointed out in these earlier papers, and we are pretty much inspired by that. So we'll say that the BDG Hamiltonian is trivial if it is smoothly deformable to either the vacuum or a fully filled state. So the previous definition is usually what is done in K-theory. And the second part of it is really saying if you have crystalline symmetries, it's good to also call these fully filled state trivial. And this is what we're going to put there. But then I've put an asterisk on the full here, just to warn you that full is a really weird concept in superconductors. In the sense that if I give you some tight band model, maybe you say there are two bands, and then the full state would be just say you have two electrons per unit cell, you fill both bands. In reality, your material always have a continuum of states that goes up to positive infinity. Right? So there's even some non-bounded states very high up in energy and whatnot. So when I say I have a full insulator or a full state in this Hilbert space, that doesn't make too much physical sense. And the usual way to do it is to imagine you can truncate this thing, and then you'll just say, oh, there's some effective tight binding description using bands up to some energy and whatnot. So that's really the thing to keep in mind when I say full, except that there's some artificial truncation using that concept. So whatever formulas you write down at the very end should not depend on my arbitrary choice of truncation. So that's the first part, which is to define what is trivial. And interestingly, the rest of the talk and something potentially more non-trivial will follow somewhat naturally. So the second part is to address how we can talk about symmetry indicators for superconductors. Before that, how many minutes? Good, yeah, I can also look at that. Yeah. So now we want to, remember that the question is to ask how we can or cannot, how we may not be able to deform your BDG Hamiltonian to some reference trivial state. So here, a smooth deformation is only possible if the representations match up on the two sides. So in my terminology or the notation we use is that the representation is represented by some band B. And we want to ask if the BDG, whatever representation is realized by the system, is going to match up with the vacuum representations. So if it's deformable, then this has to be true. It's like a necessary condition for being able to deform it. And recall that we also need to check the possibility to deform to a fully filled state. So here it's basically the same picture, except that we replace the right-hand side by the electron band being filled or being below zero energy. So again, it's only possible to deform to the fully filled state if the representations match up. And because of the funniness above defining a full state, then more generally, we'll just think of this as some possible atomic insulator in the same symmetry setting. So we have this profound philosophical statement that half empty is half full, which is just the same as saying that the full state and the empty state are really related by particle hole symmetry. So we recall that we have some particle hole operator that will take a state here at minus k and relate it to the state at plus k and plus e. So this is the action here, and because this is the fully filled state, if I apply the particle hole operator, that will take me to the vacuum. So the previous check was whether BDG has the same representation as an atomic state. And now just try to subtract out the vacuum and then replace the vacuum by this relation that is the same as the particle hole. So we're going to check this condition. So really, the statement is that we say the BDG Hamiltonian can be trivial only if the representations satisfy this equation. So BDG minus the vacuum has to be some atomic state minus its particle hole conjugate. So this is a necessary condition for your state to be possibly trivial. And for the experts, then we basically can expand the atomic states by some bases, and then we check if these can be integer coefficients. So that was the idea behind symmetry indicators developing these. And the recipe now is to say we first specify some internal symmetry, maybe temporal classes, class A, class A2, D3, whatnot. And then we ask what are the phase group symmetries in the system. And we also have to specify the pairing symmetry. So for class D3, which has time reversal, this will be just some chi plus minus 1 assigned consistently for the spatial symmetries. And then we can imagine enumerating all the possible atomic states, forget about the pairing. And we compute this particular combination of A minus particle conjugate. And now you take any reference BDG Hamiltonian, you compute this particular representation vector. And then we see that you have a topological state if this cannot be understood as any atomic state. So it's really the check. And the linear algebra part is to say you do some Smith normal form and you get these groups. And basically the claim here is that this particular exercise has been done in our paper. And this is one particular screenshot, which is some more complicated setting with some high number space groups. And not surprising, there are many more pages. So the thing, again, all the things about symmetry indicators are that they may be somewhat a little bit abstract to formulate, but then all the actual computations are really trivial in terms of computation. So all this can be done extremely easily. And session law is just how this student did all these work. So that's the first two parts. And let me end by talking about some more physical applications of these ideas, which are really applications or what are some examples of topological superconductors that we can find by symmetry indicators. So the first part is to say what happens if we just have odd parity pairing with inversion symmetry. And again, class D3, which means that we have time reversal and spin-orbit coupling. So if we work out this exercise, and it has been as well has been done by these earlier works, you'll see that in one dimension we get basically a C2 object, and this C2 is nothing but a Kitaev chain. So the trivial state would be maybe just the atomic insulator, and then the one here would actually now indicate a Kitaev chain, although that also has the real space commuting parity operator description. So that's really the power of the symmetry indicators of this refined notion of trivial states. And in 2D, what you find is that you have some weak states or weak factors. These are basically stacks of Kitaev chains on the two directions. And now you have a new object in 2 dimension. And if you examine it, the odd entries, they basically have the Foucault parity criterion. So you can see that they have helical edges. So these are the helical 2-dimensional topological superconductors. And the 2 in Z4 would be the higher order TSC. So it has some corner modes protected by inversion symmetry. And in 3 dimension, again, the weak phases. And here you have a C8 in the top dimension. And the odd entries are like analogs of the strong TI for superconductors. So these basically have an odd number of Dirac-cones. The 2 and 6 entries, they basically have 2 options. It's either, again, Dirac-cones, but in class D3, stabilized to C. So that's more complicated. But then the other option is that you can have just a second order TSC. So these will have helical hinges. And then the 4th in CH, which is like half of it, will be the 3rd order TSC. Or again, you can have just some proper counts of Dirac-cones. So really, if you have some materials, you can imagine computing these symmetry indicators, and then by finding these, or consulting these characterizations, you know what is the TSC you have. And let me conclude by a slightly more non-trivial example, which is what happens when you have fourfold symmetry. So in particular, I consider what I call D-wave-like. So by D-wave-like, I mean something like the superconducting order parameter will transform non-trivial under 4th rotation. There's a -1 here. So the usual example is just the dx squared minus dy squared pairing. So you can see that if you rotate this one by 4th rotation, you pick up a minus sign. So this is really the physical meaning of this. And if you work out the formalism, you realize that the indicator here would now be a C2. And in practice, this can be very easily computed given some normal state band structure because it can be related to just the number of field Cramer's pair at the trains, modulo 2. And the interesting claim is that this C2 here is now going to be tied to basically the quantum spin Hall response. It's like the helical TSC. So for the experts in the audience, this is like the Brooklyn parity criterion. It has been extended to like class A2 previously, but all the previous samples, they use some improper rotation. You either have inversion or mirror or the 4 bar, which is the combination of inversion and C4. Here we realize that for superconductors, when you have 4 rotation symmetry, it's just a proper rotation. Somehow you still get something that is like the Brooklyn parity criterion, and it gives you the helical TSC. But then argument for showing this is extremely different from whatever the usual way it is. So I wouldn't talk about it in this talk, but I'm happy to chat about that offline. So more physically, what this means is that this is supposed to be the quantum spin Hall phase, but now if I add inversion, then inversion would tell you that you basically have even and odd parity pairing, and then you can separate the two. So if you have odd parity, that's like the well-known case. If odd parity case with inversion, then you can just get the helical topological superconductors. And you can basically see that from the Foucault criterion. So this C4 is not going to give you anything new in that case. But the interesting case is when you have even parity, then even parity pairing would basically forbid the helical topological superconductor. But this index can still be non-trivial. If that is the case, then you can only be gapless. That's like the only consistent option. And there will be some no-load topological superconductor. And this motivates us to have this proposal, but then it's still in theory land, obviously, and you'll see why. So imagine well, it's not only because these are sketches of rendering. So imagine if some trivial three-dimensional material, maybe it's insulating and whatnot, but I just want for C4 rotation symmetry. And I want to look at the surface states. And this is some trivial thing, so I can have trivial surface states. But what is good about this setup is that I have a surface, then I generically break inversion strongly at the surface, and you can have Rushworth splitting of the banks, so you can have some enhanced spin-orbit coupling potentially. So let's say my setup is to find some material for rotation symmetry, some surface trivial states that are Rushworth split. And here's the hard part of this proposal, which is to have to bring in a D-wave superconductor. That is still more common than P-wave, or more common than topological superconductor. So that's not too bad. So let's imagine I just bring this in and then try to asymptotize D-wave superconductivity in this surface band. But due to the fact that I'm now talking about just the surface of this and inversion can be strongly broken, it's possible to have mixed wave pairing. So you can have mixed parity pairing. In particular, you can induce, by putting in D-wave, you can induce a particular channel in P-wave. And because of this index that we found from the symmetry indicator, you can show that basically in this setup with only one field, Cramer's at say gamma, then once you have this realization, then it's either a gap phase, which gives you the helical topological superconductor, or it's a gapless nodal topological superconductor. And the gapless phase is also interesting because you have exactly flat surface bound states at zero energy on one edge. So this, to me as a theorist, is pretty realistic. But I'm really happy to chat about how this may or may not be realizable. And let me conclude by that. And the quick summary is just that there's these earlier works that talk about, or recent works that talk about how you should define trivial superconductors for the purpose of symmetry indicators. Then we can compare it explicitly, and then you look at the answers, and they indicate things like nodal topological superconductivity, strong or weak, or first order, second order, the other, whatever you like. And the list may not be exhaustive. There's something new that we just didn't realize yet. And there are some interesting directions, and obvious one being which phase is which, because the symmetry indicator is some answer. You need to do some additional analysis. And I also find it interesting to ask what happens if you try to analyze the anomalous surface states and induce superconductivity. And lastly, there's probably some relations to E's talk yesterday about these biosemimentals and superconductors and being necessarily nodal. My belief is that you can actually see this from the symmetry indicators that work out. And that's it. Thanks.
A naive question about your last proposal. Does it have to be practicized by a D-wave superconductor? I mean, you can have a 3D D-wave superconductor, and the surface state is also Rushworth split.
That's also possible. In fact, let me point out that there's this earlier paper that I put in here but didn't address. So they also studied something very similar, which is essentially what you said. They have some bulk superconductors, and then at the surface they Rushbrook splitting, and this will realize this reversal. And they found exactly this kind of behavior, like depending on some microscopic parameters. Maybe you realize the gapped helical TSC, or you realize the gapless phase. But then I'm not entirely confident about the proposal in like after 10 years. The reason being they look at spontaneous rhythmic, and back then people thought it's a P wave in bulk, and now there are a lot of debate, right? So the details may have to be re-examined, but then the proposal would work. So all you really need is some Rushbrook splitting, strong break propagation. That would allow you to have P plus D wave mixing, and then naturally you have these two options once you do that. And also the counting of Kramers. So your band you have this property that in the normal state you just have one field Kramers, or one or odd. So I still think it's pretty possible. I'm really happy to chat about that.
Do any of your symmetry indicated 3D nodal superconductors have hinge states?
3D nodal in the bulk.
Yeah. Do you have symmetry? You have symmetry.
Yeah, I think that can be.
Yeah.
That is possible. Not that I know.
Okay.
So basically we have these two 3D space groups, and then you also study the possible pairing. Right? So each group becomes, I don't know.
It's like a giant.
Yeah, it's a giant table. And then we basically look at one simplistic sample, which is off rotation, and found something interesting already. So the hope is that if you try to do this more conscientiously, look at the different settings, maybe you find many things.
Has been there any attempt to apply it to real materials or realize this in different materials?
For superconductors, not yet, because we haven't even posted our paper yet. but that's the hope. One thing we found is that you never have any indicators. If you have time reversal and it's S-wave pairing, then it's consistent with what is known as Anderson's theorem and whatnot. So at least from this approach, whatever you want, you need to first say that you have an unconventional pairing. But that's usually when the experimenters turn away, right? They say, yeah, I have an unconventional pairing, then you just, like, I have good things anyway, why do I need you? That's why I thought it would be interesting to see how you might apply these ideas to the surface proximity effect on enormous surface states. And that may also be applicable to real materials.
On your question, suppose we have a S-wave superconductor. Assuming that if it can approximate itself on the surface, suppose there's some strong SOC.
Yeah, but then if you start with S-wave in the bulk, yeah, it approximates itself, it may still remain S plus P wave. But then when I say S wave, it's really talking about this chi. Like this kind of representation of the pairing order parameter, right? So whatever you can approximatize by S wave, if you don't break the symmetry, it will be in the same channel as the S wave. So it doesn't give you any possible topological superconductors that can be seen this way at least. So that's why I start with D wave, because D wave will have a channel that approximates the correct channel with P wave. So the symmetry properties.
So maybe I didn't get it. So you start with the symmetry indicators in the normal state, and then you look at the other parameter ones, like fixed, or even, and you see that they cannot be connected if you have even or odd or the odd pairing. But if you start in the normal state with different symmetry indicators, which cannot be connected in the normal state, then does that carry on or doesn't carry on to the
It may or may not. Yeah, it may or may not. So
in that situation, could you have even parity that it's still not adiabatically connected?
I don't know of any examples. So the reason being the following: if I think about 2D quantum spin Hall, which is a gap insulator, so that's what I meant by quantum spin Hall. It's an insulator to start with. You have a C2 classification temporal way. Now you can imagine adding superconductivity, and let's say it's even parity. Then the corresponding temporal wave class will be D3, which is again C2. But then the counting of helical mode is off by 1/2, because in topological superconductor, you have an odd number of helical Majorana modes.
Yeah.
If you just take your quantum spin Hall and just double it by VDG, you now have 2 copies of the Majorana modes. So actually that phase will map to the trivial phase in D3. And if you have odd parity, then the story is different because odd parity pairing, all copies of Mara animals may not be trivial. It can be a second order. So that's why the parity or just the symmetry representations of the superconducting order parameter is really important, at least for this. And with time reverse.
I have a question. So I thought there was an earlier paper by Haruki on seemingly the same topic. So what's the difference between that paper?
It's even seemingly the same title, actually.
Possibly the same title.
Right.
Yeah.
So the main difference is that that's why we began by acknowledging these works. Yeah. So basically, it's.
But it's not. It's one of these works.
No.
So, not one of these works.
Yeah. So
okay.
that's why
That's
this is
what I
really
thought,
what motivated this new discussion.
Yeah.
So in Haruki's earlier works, they define trivial superconductors using roughly what I call the band definition,
Yeah.
such that the type chain is not detectable.
Yes. Okay.
Right. And then these new ideas to say you have to do a better job in defining
Okay,
what
so
is
it's
trivial.
kind of, okay, I think I understand. So the earlier Haruki paper is basically the same thing that you just said, but with a different definition of trivial. And then that plus this is kind of giving you the upcoming
That's
paper. Okay.
Yeah. And in these earlier versions, you don't detect things like a type chain or
Mhm.
these corner modes GSC. So
Mhm.
those are obviously interesting. And actually, what is
But-
funny is that you
yeah.
don't even detect the C4 rotation phase.
Mhm.
But that is not even corner mode, right? So there's some new
Mhm.
new things that you gain by proper definition.
Yeah. Is there any, okay, but now that we have some enlightened view of different, let's call them levels of topological faith, like, can you systematically see what was missed by the earlier paper, and might it pick up on like all phases with edge states? I mean, I guess a lot of it's missing type chain.
Yeah, and then
Like, is it picking up on stronger stuff or just different stuff?
it's, I would say different because
Okay.
in the inversion examples, all you pick up by this refinement
Mhm.
are corner modes in different dimensions.
Mhm.
But then for the four-fold rotation example, you pick up the helical
And you
which
just
has-
totally missed that before, and that's
Exactly,
completely anomalous.
Yeah,
and
it was kind of a surprise to
non-trivial.
us.
Yeah, okay, I understand, yeah, that's super interesting. Any further questions? Okay, great, thank you.